All right, here is what I call the emitter effect, and it's obviously a bit more complicated than the randomizer effect, and probably the fantasy effect. So I think this is good to dive into when you really start to have to deal with the spaghetti that can be a node graph. But let's see what this effect does real quick. All right, so far not much. We've got a title treatment up here, and our model here is throwing up hairballs that transition us into a room with, oh, who's behind her? It's a cat. You can't see it, but behind her is a cat jumping up and down on the couch, and the emulator isn't going to let us get around to see that. What you also can't see is that there's a bit of parallax with the cat. While it's continuously jumping up and down forever on the couch, as cats do, it's also a bit tied to the X and Y position of the person using the selfie. So there's a little bit of parallaxing. The cat will never leave the couch fully or fully go off screen, but it just kind of stays on the couch jumping up and down slightly relative to the viewer's motion. And that's what's going on. So I thought this was an interesting effect, both because it's a real effect and because it demonstrates a few principles that are a little different than a standard kind of randomizer effect. There's this transitional element, there's segmentation, so you can put yourself in the background of something, and also animated elements as well. So let's walk through all of that. So a slightly more complicated scene hierarchy here than the randomizer, but the focal distance, ambient light, direction light, still the same, never messed with it. One thing to note on the camera here, you see you've got an indicator that you've got an output patch, and that means if you go over here to your properties, you've got the texture extraction and the segmentation extraction. So you know that this is going to be a segmentation effect, and that those textures are going to be available to you right here. Coming down, we have the TT canvas. The canvas is just a holder, and on it is the title treatment element. TT is for title treatment, kind of a common acronym in marketing and ads. Then we have the holder for that explosion that happened, which is an animated sequence. You can see that the visibility has a patch for it in that node graph somewhere. Then we have a replay holder. We have a replay button so that after users have had this happen once, they're not stuck in the room. They can replay the effect. Well, that's my own voice providing that. You see there's an animation to it as well. It rotates in. And if you tap that, it should restart. Oh, the timing was perfect. Okay, so we've got the visibility on the replay holder, but also the replay, you'll see there's a patch for that rotation. The face tracker is holding a mesh that has all of the hairballs. There's a holder for it, and then 4 individual emitters. Why not mix and match? Well, because each emitter only takes one material. We'll break down the properties in just a second for the emitter, but it just takes one material. So to have multiple colored or multi-textured hairballs coming out, I have different emitters that all are active at once with slight variations in their settings so that you have some variety of what's coming out. And you can see that the holder, the hairballs are tied in their position to where I wanted them relative to the face mesh. Let's see if I can get a slightly better view there. See the emitters, when they actually start doing their physics, given this placement, look good for coming out of the mouth. So taking a look at the properties of these emitters, you can see here they have a type, point line, plane ring. This is just about how they tend how the particles tend to spread out. Point works fine for me because I'm wanting them to come out of a single point. But you have options there. World local space doesn't come into play with this effect particularly. I keep it in world space. Your birth rate is going to be a big part of how much is coming out of the emitter. Also the speed. The combination of birth rate, speed, and lifespan are a big part of the performance of emitters. It is a physics-heavy, real-time kind of simulation that the AR platform runs. So if you start to see some sluggishness or it gets a little chunky, I would look at adjusting your lifespan first. The lifespan is related to how long the AR platform is keeping track of and doing any math on each particle. So for the lifespan, the shorter it is, the less computational effort is basically happening over the span of time on behalf of the meta. Spray angle, pretty self-explanatory. Just you play with these values to get the kind of angle that you want in the X and Y axis in particular. The particle, you can make them larger, smaller. Billboarding is a way of saying that the particle will always face you. So when the particles come out, they could be twirling around. And if you have it billboarding, the face of it will always face towards you. So if you have a 2D element and you don't want any funkiness as it spins around, where it starts to become invisible as it goes flat on its plane or it's on its axis, billboarding will always keep it looking towards you. Spin and tilt, if you want to give it some of that more fun twirly behavior, you see it's pretty low. Shape, the shape of the particle that's coming out. I have it on a plane because it's just a billboarded 2D image. You could, if you didn't care about having that nice hairball-y texture, just make them spheres. And that would probably be, that might be computationally easier on Meta, I'm not sure. But that's an option there, and you've got other shape options as well. These, when you choose them, a benefit of these is that whereas I'm using a texture element in the emitter, if you use one of these predefined mathematical shapes, it's not going to add any weight to the effect. So if you start creeping up on your effect size, one way to deal with that would be to consider using a built-in shape, a built-in kind of primitive, instead of using a textured element for the particle. The material hair one, I use mat underscore what have you to designate material so that when I'm looking at a big long list of things, I know right away I'm looking at a material. I don't have to know what category I'm in. It's a material. So there's no reason that you have to follow that. That's just a naming convention that I stick with, and you're welcome to adopt or ignore. Acceleration, these, because I want that downward hairballs falling down and filling up from the ground, I accelerate everything down on the y-axis a little bit with no drag, but you could, and that would change the quality of what you saw coming out. Would introduce a bit of delay, which I didn't want to do. I just kind of want a fast output falling down. Coming back over here, we have the Philip plane. And that is that singular collection of hairballs. If we restart here, we'll see them come in as soon as our model here deigns to open her mouth for us here. There we go. There it is. So it stays invisible up until it's needed. Then it comes in, and there's a very fast moment where the animation for the explosion plays, and the plane disappears, and the explosion disappears, and the background appears with the cat. And we'll get into how all that's controlled in the node graph. Part of the complication of the node graph is just making sure the timing of all of that is right. Here's a segmentation canvas holding the person in the foreground. And the placement of this in the scene hierarchy is important. If you start messing with where this is, you'll start to see where things pop up in front of you, no matter what you do. Now the background canvas, that's where our cat is, and you can see the position is being controlled in the node graph. Specifically, it's always going up and down in the y-axis, and it will move on the x-axis a little bit relative to the person selfieing. And our background, and that's just a static holder for that room, just an image size to be in the viewport. We have the explosion sound, and that's controlled in the node graph, which we'll show. We want to make sure that it is audible. This is checked. Interesting here, I call this puke holder. Apologies if that's an offensive word. Sometimes people don't like even the word, hearing that word. But this is a little bit unique. You see there's a patch for it that controls the visibility of it. What's that all about? Well, that will come into play when we're in the node graph, and I'll talk more about that. And then we have another similar audio controller for that sound. Over in our assets, the materials, we have the transparent face. This is just a material by default for the face tracker face mesh. And we don't want it to do anything or adjust the user's appearance in any way. So the opacity on it is all the way down. We have the fill up. So that is our plane with the hairballs coming up from the bottom. Segmentations. The background, just the room. The material for the explosion, and so forth and so on. And then in the textures, you see the segmentations I mentioned earlier. The full background. That replay button, that texture for that. And the explosion sequence, which is a 17 frame sequence. That'll be important a little bit later when we're going through the node graph. We have a couple of playback controllers, the explosion and, puke. We see there's an animation sequence controller. And you just saw me realize that that other animation sequence wasn't being used. And I deleted it and it restarted. Looping animation. So this is not something that I made. This was brought in from the Spark, the AR library. We'll show that when we're going through the node graph. And then the actual files themselves. One thing to notice real quick is the explosion and such, there's playback controllers for that, don't have any patches associated with them here, but we will see them in the node graph. All right, the node graph, let's get into it. So right away we see we have this special little box, instructions on start. Two things here. One, the instruction itself is localized if you use the timed instruction patch, meaning this will automatically be translated into different languages without you having to do anything if it's one of their built-in instructions. The other is this pulse. If you have this enabled at the start, then as soon as your effect starts up, this will trigger right away. You don't have to feed it anything into the initial pulse. It's just going to turn on as soon as the runtime instantiates. And then it will show this. And this is pulled as a project capability in here. So in your instructions, as soon as you add that patch or node, it's going to add this into the project capabilities, and then you can drill in. See, this shouldn't be grayed out, but it is. This will be checked, and then you can add custom instruction. I've chosen open mouth to start. And it gives you this token here. And that token is what you're looking for here. So you could add more, but in this effect, it's just opening the mouth. And I want to let people know, if you open your mouth, something special will happen. And it will play for 2 seconds. So that's an important bit of UX if it's something you think that your effect will need. Everything starts off with finding a face. It's a built-in node that you get just from pulling it in like that. Once it sees one, which is 0, So quick aside, and if you're going through the different templates, I apologize. You'll hear me repeat myself a fair amount on some of this stuff. But if you're not familiar with programming, it's totally okay. One thing that's common in programming, though, is that when you have a collection of things together in a list that you want to go through, and in this case, let's say meta is always trying to find a face. So there could be multiple faces, and it's always tabulating, okay, how many faces do I see? Well, I'm just going to operate on the first one. In that case, it's actually going to look at the zeroth, the naught element in that list of faces it sees. In programmatic language, often the first element in an array in a list of things is the 0 element instead of the 1 element. So the 0 is the first element, if that makes sense. So in a list of, I've got 10 options for something. In programmatic speak, that first option in that list would be the 0 element. It would the list would be 0, 1, 2, 3, 4, 5, 6, 7, 8, 9 instead of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So it's a little funky, but that's just how it is. I mean, there's a reason why it's that way, and there's a history to that. We're not going to get into that here. What you need to know is that you tend to need to subtract 1 in your mind if you're needing to pick from a list of things and you're referencing that in a node, or you need to do some sort of addition early on so that you don't have to think about that later where you're adding 1 to something, and then you can treat things like 1, 2, 3, 4, 5 instead of 0, 1, 2, 3. So it sees the first face that it sees. It does a couple of things. It outputs the 3D position of that face it sees in the X, Y, and Z axis. Look at that really quickly. You see how there's a Y, X, Z. Z is the one that people can get confused with when they first start using 3D space. That means, towards you and away from you. And Y is up and down, and X is left and right. Not every program works that way, and some let you kind of adjust that or change the orientation of the axes. But that's how Meta works out of the box. And it also outputs information about the face. It's looking for, what is the face doing? One of the options it can look for is opening the mouth. And we're going to go through, and we're just going to kind of go by what each node does and follow each trunk or pipe or connection, however you want to think of it, down until we have a good understanding of what's happening here. So as soon as it sees the mouth open, it has a couple of options. It can gauge how open it is. So you could create a range within which it does things, or after it reaches a certain amount of openness, it does something, or vice versa. It also is just looking to whether or not it is open. In this effect, if it is open, several things happen. All of the emitters for the hairballs turn on. You can see right now, by default, they're defaulted off. That's going to change as soon as it sees an open mouth. You'll see those check on. And I'm going to drill into what this does. This is a subgraph, but we're going to go through the whole flow here and then come back to this. So then, after that opens, or as that opens, a pulse is sent out. And the pulse is just a way of thinking about data that's going from one function to another, saying, this just happened, this just happened, this just happened. So a pulse says, oh, this just happened. And it hits a few things. And we're going to go through all the three turn on stuff first. First things first. It goes to the single clip controller node, which controls an audio player with that hairball bleh sound and plays it. It hits the play for that. Also, that pulse says, now start a delay of about 2.5 seconds. After that 2.5 seconds, a few things are going to happen. We get a slight delay after that, there's a reason, and I'll explain it, in which we get a turn off command to that collection of hairballs. In other words, after that delay has passed, that means that hairball plane is all the way up and it's time for it to go away. After that delay, we also hit this switch with a turn on pulse. Turn on what? Turn on the explosion, the holder for that animated explosion you saw. And let's send out another pulse. This is a turn on pulse, and that turn on is going to carry through. As data flows through here, all of these, what are ultimately actually functions, understand that this is a turn on pulse. And it's going to hit the play for the explosion. The explosion canvas is on, and the explosion sound plays. And that delay, that interplay in the delay, this delay has to do with when we want to time when this is visible versus when this needs to be visible and when this needs to play. So it's making it all work together so that you have that seamless experience of something happens to transition you into this other state, and the audio for that also plays in the correct timing. In addition to sending the play out here, it also sends a 0 delay to an animation to play the explosion itself, a 0 delay. This is not something that I use actively in there. Like, there's no trick. It's you see it's 0 duration, so it's not doing anything. But I wanted to put this here because it could serve you as you change stuff and play with the timing of things. You might want to delay right here before you actually play through the animation. It really depends. So this is kind of a random thought starter for you if you want to really adjust this effect to your own needs and you want to change the timing of things. There's a lot of delay nodes in here, and it's a dance, and you got to figure out what the dance is that works for you. So that plays, and just a reminder from what I was saying earlier, there are 17 frames, which we saw earlier when we looked at the texture for it, the animation sequence for it, I mean. And the first frame starts at 0, which is the first frame. There is no 0 frame. It's just that 0 is the first element in this list of frames that it's created for the texture sequence. That's how that's working. So backtracking here, we don't want to forget about this connection. That hits a turn on pulse, and a few things happen all at once here. We get a not signal to the hairball and puke holder. So we negate that turn on and therefore turn off those holders. That's a timing issue. You saw that delay stuff. That's so that when that plane starts to come up, that those emitters aren't still going and pushing through the plane. And we have that turn on pulse down here playing that animation, shooting up the Z rotation. So rotating, you see this blue arrow right here? Rotating around. That's how you get this to make this. This is a Z rotation. It would look significantly more funky because it's a 2D element if you had it on the X or the Y. We just want to rotate the Z, give it a full rotation, a 360-degree rotation. So just to be clear, when we hit play for 2 seconds, each tick of the animation that goes by gets multiplied by 360, and that gives us this spinning around the Z-axis up to 360. And just to be clear, let's show just how this animation works exactly. When you hit play, let's restart this. Watch this value. It's fractional, so those fractions are getting multiplied by 360 up until it's 1, which is 100% in the animation node math, times 360, which is 360. So we get a full 360 rotation. That lets us get the replay to turn around all the way once. Coming out of our animation here, we're going to backtrack all the way here. And look at this delay, the final element of this turned on pulse. We have a 0.2 second delay, very short, but that triggers a 4-second delay to the top part that we saw. where we take the start and end value of the progress of that, and we negate the y-axis. You see it's expecting an x, y, and z, and we need to send it a value somehow. And because it's expecting what we would call a vector 3, which is 3 numerical values that are going to be used in x, y, and z in this case, we can just pipe a single value out of here right into the y-axis. So these don't get touched. We're just pushing the plane up. Let's watch this real quick, just to make it really clear. Here it comes. So it starts, you see that plane starts in a negative position. It's way below the focal plane down here. By negating it, we give it a positive value and it brings it up to 0. Because eventually the progress will equal 1, which is 100%. So by doing it fractionally and negating it, we are coming from the bottom and then going up to 100%. You're eventually going to end up with 1 as your final value. 1 negated gives you 0, which is where you want to be totally aligned. Hope that makes sense. It's a little funny, but if you keep playing with it, it does become visually, it starts to make more sense visually. We also have a greater than giving us a pulse that turns on that fill-up plane in the first place. Now, why wouldn't we just pipe this to this? In fact, when we try, we get the red connection and the inputs just disappear from the node. What's going on? Well, what's going on is that the value coming out of here is a number, but pulse expects a type of data coming into its function that is not a number, but rather more like a Boolean value, which is a true or false value. In other words, you can use logic nodes like this, which determine if something is true or not. In other words, is this value coming out of here greater than the second input, which is in this case is 0. Remember, this is starting from a fractional amount, but less than 1. So as this raises, it's immediately going to be true that is greater than 0. It's a fractional amount, but it's not 0 or less than 0, I should say. So that becomes true right away, therefore giving us the pulse that sends this out. So when you can run into this a lot, where you need to convert data types. There are different ways to do it. This is kind of a quick and dirty one. Taking a value, comparing it to something so that all we're expecting to get out of it is a yes or no. And we can easily pump those kinds of things into pulses. And that completes what's happening with all this work in the pulse. So what's after that? Well, all the rest of the complication you see is about what happens when the user starts recording the video or taps the screen and does that replay. Replay here, also video recording here. This is a built-in node you can access for the camera. This is what this is indicating as well. So we won't go into as much detail about these because it's just hitting reset and stop for things you've already seen. But as soon as you tap that replay or you get the pulse from the camera producer saying, yes, the video is recording, let's turn this on, that means we want to make sure that this stuff's all gone. The replay, the background, the cat, it all needs to be back to scratch. So we send pulses out, also including pulse merges, very convenient utility, to reset, to turn off, which remember in this case turns on this stuff, but turns these off. Sends an off pulse. Remember that these nodes will remember what the quality of the pulse is coming to it. It'll know if it's a turn on or turn off node. So that turn off command will flow down to this turn off. Therefore it knows, oh, it's a turn off, I'm going to reset. And it just, all of this piping and stringing along is just hitting that stuff so that you get your appropriate turn offs. Your appropriate turn offs, that's an interesting turn of phrase. And that's it. This little spaghetti mess is ultimately not that complicated. It's just about figuring out the timing of how you want everything to flow, and then figuring out how you want to reset your effect if that's functionality you want to offer in your effect. But finally, let's get into our cat movement. You can see here with the effect running that we are being fed vector 3, x, y, and z values. And if we open up the subgraph, we see something not too complicated, but we do see some funniness here. No matter what you do, sometimes meta will surprise you. So we have the information from the face tracker coming in here. It's getting unpacked. We're popping out the x, y, and z values that were coming in. Let me get a little bit closer here. And then we need to, if we want to add a subtle parallaxing effect to the cat, we need to translate the values that are in here into the coordinate plane that's happening in this viewport. So that involves multiplying it by a fairly large number, and then to zhuzh in things just where we want it to be, offset from maybe the left of the screen, we need to give it we need to add a hard value to it. And then to make sure the cat's not flying off the couch on the x-axis, we clamp it, meaning we confine the values that come in to operate between a minimum and a maximum based on the user's position, which here is just never going to be within the range because of the emulator and the fact that this person isn't really moving things around. We can start to get an idea about things if we start to really mess with it, but the emulator is not good for this. This is where emulating it on your device is a good idea. And then this ends up being a value that we pipe back into a vector 3 node that has is ready to receive x, y, and z values that will get put back into the cat's position in the x. For the y, instead of building out a complicated looping animation, I did just pull this in from the AR library. Pulled it in, typed it in, says looping animation, and somewhere in here there's going to be view all, yeah, and there's a looping animation patch. So I just clicked that, imported it, and then that was just available right here. Dragged that in and chose to make it a floating, so it's a cat floating technically up and down. The amplitude and frequency will let you fine-tune that behavior, and then you see the output options are rotation, scale, position. In this case, we're just jumping up and down, going up and down on the y-axis. So we're seeing that come into position. Floating just affects the y-axis values. We take that out of y. We put that into a subtract node to fine-tune where that cat is in position on the screen. So it's always this is another way of kind of clamping the value. And we feed that into the y packing node. And that's how we get our constantly looping y value. Back to main. And that is it. That is all the news that's fit to print if we still printed the news.